So in here, for gradient descent, it's more about quality. For each updates, we go through our data. For each updates, probably it can give us a better updates. But for stochastic gradient descent, it's about quantity. We just a few, just one sample for this algorithm. Of course, it also will incur unstable. For this instability, you can also like use mini batching, one batch to update one time. There are different design choices. Okay, this is the difference between gradient descent and stochastic gradient descent to optimize the loss function of a given machine learning algorithm. Okay, okay. So what we have right now, they're all about linears. But the thing is, we know, assume we are want to do linear models. We know that linear models, we one dimension feature or two dimension feature, we're all given. And then given these linear models, we can have this different bunch of loss function as our optimization target. And then given this loss function, we can simply use the gradient descent or stochastic gradient descent to optimize. That's it. Is this word so easy? Of course, no, right? These are linears. Linear. This word is not the ideal word. It definitely is not linear. This is not linear. But if we encounter non-linear, what should we do? And of course, even you are doing linear, how do we come up with these features? In fact, if I'm telling you we're given these features, we're using linear models, in fact, the problem is solved. Given so many on-shelf algorithms right now, we do not need anybody to solve it. We know how to solve it. Just call for the on-the-shelf algorithms, right? There are a bunch of different algorithms you can use, but the problem is how do we get the features? If you encounter a problem, you encounter an application, how do you organize these features? So today I will continue to introduce what is feature templates. And in old machine learning, we also call that is feature engineering. And I will just illustrate a simple idea of what is feature templates. And then for nonlinear features, before we get into these complex deep neural networks, how do we deal with nonlinear features given our linear models? Okay, at the beginning, we don't have the linear model. We don't have the neural networks. We just give a new linear models. Whenever you encounter nonlinear features, what should we do? So this is the second part I'm going to introduce. And if we have enough time, we'll go into the unsupervised learning. Okay. So what we cover so far, we abstract a hypothesis class. For classifier, it is a side function of the score value. For regression, that is just a score function. So given this assumption, we can come up with bunch of choices. And we're given the loss function. We have the data, we have optimization. We can fundamentally go down to here. But the problem is how do we decide the data, the features? They're all best domain knowledge. We select the features with our domain knowledge, or probably just use some exploration algorithm, right? And so if you have good data, if you have a good assumption of the predictors, you can use good data to train it. But if even though you have good data, it just give the bad assumption of predictors, no matter how large data you have, you may not can give a very good predictor. So these are different aspects of how to solve a problem. Good data with good features and the good assumption of the models. And then your loss function and train, right? So let's take a look at a particular example. Assume we give you a string, and right now I want you ask you to design a binary classifier. Given this string, I need to have a very good classifier. Tell me that if that string is an email address or no. We need a classifier. Of course, if we don't consider this part, we have this part, right? We can design a word vector and feature extractor. And this feature extractor will give a bunch of training samples. This can be 5 dimension, 10 dimension, or even higher dimension. Depends on how you represent your data, right? And given this classifier, you can train it, you can design, you can use this hinge loss, logistic regression, or the loss function to optimize to get the weight. And then this classifier can tell us if this string is a valid email address or no. This basically binary classification, right? But given if give you a string, what kind of pattern is seeing that is an email address? What are kind of features they are related to predict this input is an email address or no? Just like if you want to classify an image of a dog, that is a dog. Basically, what patterns you capture, that this is a dog. These some features you want to extract from. What is that? What's that? Yes, this one pattern, right? Like polyu.edu.com. There's some specific pattern that reflect this string is an email address. So what we need to do, we need to identify what kind of patterns they are relevant to predict this label Y. This is something we are going to answer. So for this particular example, given this string, so right now we don't know if that is string or not. Of course, right now you know, you're a human being. You have a prior knowledge, no. This .com Gmail is an email because we know, we have been trained. If you are a younger baby, of course, he or she does not know. But we have already, we are trained, given a string, we know that is a valid email address or no. For machine learning as well, they need to be trained. But what kind of pattern to be trained to this model so as it can predict this string as an email. So we can extract the feature. What is feature extractor? The length of the address, the string is larger than 10. Indicate one number. This is a bunch of feature name, and this is a bunch of corresponding value that we define given our prior knowledge. And the fraction of alphanumeric, that's 0.8, the fraction of alphabetic among the string. And it contains a particular character, at. Email address, always there's an at in there. So yes or no, indicator. And ends with com, yes or no. And ends with something. You can see we can define a bunch of features and we just give the feature with the feature value. This is our predefined feature name, feature value pairs. Of course, when you are training a model, you can just treat this as just like a comments for code. The model will not recognize this. The model just wants this value, this bunch of value. These are feature values, right? So this is something that, given the problem, what you're going to do, you need to identify what properties of this input that relevant for the predicting label Y. Okay, so this is what this feature extractor for. And this is also the old machine learning user that use feature extractor or descriptor. And some people that like probably 2 to 3 years ago, when deep learning is not so well known to other domain, on that, of course, computer scientists, they know using deep neural network that can extract the features automatically. But if you are from other domains like physics, like chemistry, they will predefine these features first to represent their data first. They're given using their domain knowledge. Just like what we do right now. Okay. So in here we can design a corresponding weight vector and feature vector. Feature vector is something that represents the data sample. Weight vector is something that we have got from the model predictor. So if we plug in, we do the inner product, what's the meaning of this inner product? This given our previous defined sort of score function, which is defined as the inner product of the weight vector and inner product, which is formulated as the weighted sum, the weight, the aggregate inner product of each particular dimension together. So what's the meaning in here? If I have the weight vector linear models, what's the particular weight for a particular feature? If you have a positive weight, means that this positive weight have a positive prefer to have a positive outcome. Okay, this is what we call weight in the product of the feature vector. So this assume we have already represent a bunch of samples given this data representation. And then we can train a predictor, and ultimately the training algorithm, learning algorithm give us this weight vector. Then we can have the score of a particular sample in here. And we can have the score value of particular sample. Okay, okay. And so this is a conventional machine learning. Usually we will say this is a interpretable machine learning algorithm. What's that? Because whenever you have outcome, you will know as the weight, this specific weight that contribute to the feature. For example, this feature with a positive weight means that this feature has a positive contribute to a particular prediction. If that is a negative, means that that has a negative contribution to the predictor. This is what we call model interpretation. Have you heard about model interpretability? Transparency. In fact, today I have mentioned two aspects of trustworthy machine learning, trustworthy artificial intelligence. One is machine learning security. There are a bunch of people, they're working on attack and defense. Of course, these days, people talking about large language models. People, they're talking about how to attack or defense while using large language models. And in here is the interpretability. How do we know particular feature contribute to the task? Like if you're using a large language model, you have input, you have output. How do we know what kind of pattern that extracted by the large language model so as it can give us this kind of outcome? This is something want to give us explanation or interpretability. Of course, linear model is simple. We can just look at the weights. We know this particular, the weights, that's negative 1.2, less larger than 10. This is not so important feature. To predict the string is an email. But if that is an 8, that is a very, very significant feature. So you can see the weight value is 3 is large. Then it means this particular feature is very important to classify the string into an email. This is what we call model interpretability. You will know a specific feature, how important it is to the particular outcome. Is that clear to you? So in here, even though I didn't very, very specific introduce what is machine learning interpretability, but still, by using this linear interpretable model, I want to tell you, this is what we call interpretable AI. So if you are using large language model, you have income, you have outcome. That is a black box model, and they have a billion parameters. You have no idea what is the model capture from the input, so it gives you outcome. It may not be trustworthy, especially when using this model in your very decision critical applications. For example, use the model to predict if the stock is rise, is increase or decrease. Buy in or buy out. Will you trust it or no? It is not interpretable. You may not trust, right? So, but in here, You very, very easy to understand because this add is critical to identify a string is an email address. So this model can learn a very high weight for this particular feature. This is what we call model interpretability. Okay? Okay? And for example, the .com, this is also a very critical feature that predict a string is an email address or no. So that's why in here, we learn the model that this model can give a very high weights for this particular feature. Okay? Okay? So something that we just ad hoc, based our domain knowledge, we can come out with a list of features and give the sample with a feature name, feature value pairs. Then we give this bunch of samples. We can use our linear models we have learned, and then use a learning algorithm. We can train a linear model to identify if last string is an email address or no. All right, but we need to something that is an organization way to design features. Usually, what the feature we can include. So this is what we call, we need an organization principle. Feature templates. Feature templates, conventionally, people like you that call that is feature. A feature template is a group of features all computed in a similar way. In fact, by this sentence, meaning you can think of that we want to design something that can capture some certain patterns. Not a particular pattern, but some type of patterns. For example, we can use an English to describe. Still in this application, identify a string is an email address or no. We can use an English to describe last 3 characters equals to this brand we want to fill. This is what we call template. We want to fill something in here. There can be ends with something. This is our feature, list of features name. These corresponding feature values. So in here, we are not define a specific feature. For example, include a specific one, a specific character. No, we want to define a specific pattern, types of patterns. The last characteristics equal to something. Okay, so let's take a look at the example. Given this application, we have 3 different types of feature templates to define the features. For example, the last 3 characters equals to something. And we can have the feature equals to .com. We can define. Given this bunch of data sets, as long as the last characters that equals to this .com, COM, then the value of this particular feature is equals to 1. If this string length greater than something, we use 10 as a threshold. As long as it is greater than 10, then the value of this template will be 1. And the fraction of alphanumeric characters leaves something that threshold. We define the string, the input string. We can say, okay, 0.85, this have a high possibility that be this based on domain knowledge, of course. Okay, let's give you a computer vision example. Remember, we talk about the binary, the classification of binary classification or regression problem. We talk about a poverty mapping given an image of a particular region, that we have the location of where we take this image. Given this image and its location, we want to classify the poverty of this region. So this is a image problem, right? Image classification problem. So in here, we can design the feature templates. So given an image, usually what kind of features we can define? What are information we can extract? Yes, the pixel value, pixel densities with different channels. So in here, you can define a feature template. The pixel intensity of the image at the row and column. Different row column. In fact, that's if you're using deep neural network right now, for an image, we can use a 255 multiply 255 pixel value of image of 3 channels, right? So in here you can define templates contain this feature at a specific row and column in red channel, the value, the specific pixel intensity of the image. That's one part of the feature template. And we also can define the location of image by using a bounding box, a specific location of an image. This is one particular feature that we can define. Okay, of course, this is all feature engineering. If you are using deep neural networks, you just present the pixel value back, the image, the matrix of image. Each item is a pixel value of the image. That's it. That is simpler. This is something when you're using linear models, you will need to predefine the features first. Okay? Okay. But for a string, you can see you can define, if you're using these feature templates, for this particular sample, we can give a bunch of value to represent this sample. Just for this simple, very short string. If that equals to with an A, B, C, D, F, G, the last character equals to something, end with something, we can define a bunch of values. So you can see, if we're doing natural language processing, there are many features, they are all 0. That's what we call sparsity of the data. So in here, we will not represent, we will not use all of the features at the same time. Our representation will be use the dictionary with a more compact representation. Use a dictionary, key values to store the features. Okay, okay. So this is what we call 2 different visual vector implementation. One is dense, the matrix representation, or we call arrays. When you are doing image computer vision, usually we use arrays. There's a dense computation. But for natural language processing, usually the data is sparse. We will use a very more efficient, not efficient processing, but efficient storage of the sparse representation. This is more in natural language processing. We use the key value store, the dictionary, to store the features. It is not so efficient to process because for an array, we can easily use the GPU, right? The GPU, the TensorFlow, the framework. It is very well used to deal with the arrays. But for the sparse representation, one bright side is the sparse storage, but the downside is the efficiency to deal with the sparse representation. And the other bright side is you can dynamically to add the features, to update the features. Okay, this is more aligned with the data structure you learned. Dealing with arrays and dealing with dictionaries, they all have different downside and bright sides. Okay, okay. And for these templates, we just want to design an organization way to describe the data. This is what we call feature templates. But still in this stage, because we are talking about the advanced AI, which is deep neural networks, usually you would not need to get usually people that just play with the models. What you can use is just download the ownership data sets that people have already extracted features for you. But what if you want to play with your own applications? Now you collect the data yourself. You will need to clean the data yourself. You need to extract the features by yourself. Of course, the features, usually they are domain specific. And this part we call that is feature engineering. Okay? Even though you use deep neural networks, still you need to present the good data. Only you feed the data, the features that are relevant to the task. You can train a good model. Okay? Okay? And the feature engineering is one of the most critical components in machine learning. And usually that is domain specific. And even though when you are using neural networks still, you will need to give the model good features. Of course, if you're using linear models, you will put more efforts to extract good features. Okay, when the learning model itself, it can also, if it is okay, that you probably can extract some not so relevant features. Ideally, the learning algorithm will just assign a low weights to some irrelevant features. Okay, this is about features. All right. So, as I mentioned, we're given the linear models. What if the features non-linear? What should we do? Suppose we haven't have, of course, we haven't have any knowledge about neural networks. We are dealing nonlinear features. How do we just use the machine learning of linear models to deal with our problem, to deal with these nonlinear features? This is something we're going to address in the following time, okay? So let's recap for linear regression. We are very simple, just design a linear model with the inner product of what vector with a feature extractor together. And given this potential data samples, this learning algorithm will give us a predictor. This predictor can give a corresponding outcome. So the hypothesis class in here, the regressor, they are all linears. They are all linears. This what we covered last week, right? But what if we have given a bunch of data samples, they are non-linear? What should we do? You can draw a line in here or there or here still. No one can fit this bunch of data samples. What should we do? How to address this kind of non-linear samples? If you just manually to draw a line, there's probably something curved in here. And respect to the variable as x. And in here, x still, we still look into the one dimension variable. What should we do? Suppose we just know the linear models. We just have the linear model knowledge. Let's take a look at this feature extractor. So instead of use 1x as our feature extractor, we add one more term, x squared. This is our feature extractor. So for given sample, x equals to 3. Then our feature extractor will be 139, right? Assume we can give these 3 different choices of our models. For the red curve, our weight vector is 2, 1, negative 0.2. 2 is our slope. 2 is our intercept. 1 is our slope, right? And negative 0.2 is our curvature. So we have a red line here. Of course, we have the purple choice. Our intercept is 4 in here. This is purple. And the slope is negative 1. And the curvature is 0.1. This is our second choice. If the last dimension of the weight is 0, then we down to the line. The curvature is 0. This is our third choice. So in here, we can abstract our another hypothesis class, which is still the same thing with the inner product of the weight vector with the feature extractor. Is this still linear in here? Linear with what? Linear with what? This we still use our previous hypothesis class, linear. We have two components. One is weather vector, the other is feature extractor. What we did right now, what we change right now, it just change the feature extractor. Just add one quadratic term of the features, x squared. We just change this feature extractor to deal with these nonlinear features. Right? This is what we call quadratic prediction. And in here, x is just one dimension. We just add one x squared as our sort features. But what if the x have two dimension, 3 dimension, 4 dimension? How many terms we need to add up on this feature extractor? How many terms? What's the complexity? If x is d dimension, be all d squared, right? To deal with these nonlinear features. So that's why we will need, we x is a very high dimension input. That's why we need the deep neural network to deal with this kind of problem. That's why deep neural networks is so powerful. Okay, not linear models can deal with this kind of high linear problem, high dimension problem. Okay, even though we can just change the feature extractor to deal with the linearities of x of the input. Okay, so this is another predictor, piecewise constant predictors. Let's look at. So we can design the feature extractor and deal with different regions we have to represent the variable. This is our variable x. For each region, this is our y. And for each, in here, if we just simply use our linear models, how do we do to fit the data? This is how we visualize the training data we have. And if the data is located in the first region, for the red line here, it can be corresponding to the corresponding weather vector. This is a piecewise constant. Each region is a constant. So we can design have a corresponding weather vector to design this kind of piecewise constant predictor. And if you look at it very detailed, you can see for each corresponding weather value is a predicted value of that region, right? So if for a red line, if you locate it in the first region 0 to 1, then the value is 1. It's 1. For this region, the value is 2. It's 2. For this region, the value is 4, so on and so forth. We just simply partition the input space into different regions to approximate this piecewise constant curve. But still, if abstract, this predictor is still the same as what we defined, linear models. So, is it still linear? Yes, it is still linear with respect to the weather vector. It is still linear to the feature extractor by x, but it is not linear with the variable x, right? But still, for this complex problem, we just simply partition the input space, represent the feature extractor in this way. So you can still use the linear models to represent these so-called piecewise constant predictors, right? And what about the periodicity structure? If the input variables, they are related to time, we can imagine usually this predict the outcome. They have the periodicity feature. For example, traffic, we have daily patterns, right? Sales, we have annually patterns. So if we have these time variant features, then what should we do? You can just have some periodicity pattern term to capture these trains. So you can simply do add up this cosine in here as one part of feature extractor. This also your domain specific. Because your application in here, it input data, they probably time variant, they have some periodicity pattern, then you can simply to add one more term that can capture the trends. And given this feature extractor still, you can use your linear models to capture this kind of periodicity patterns. Just throw all the features you want to learn the models. So these three different bunch of predictors I want to tell you, even we have linear models, we still have the way to solve the linear features, like the piecewise constant predictor, the periodicity structure predictor, right? So these are for regression, for regressor. Okay, so was it good? In here, we just want to illustrate some idea about even using linear models. You are not can deal with linear features. You can still deal with non-linear features by simply change the feature structure. And for the loss function, for the optimization algorithm, this can still remain the same. And the model still linear to the weather vector, still linear to feature structure, even though it is not linear to the input variables. Okay? And so, but what's the bright side of linear model? Just guess. What's the benefit? If you're doing linear, because it is linear respect to what vector, if you're doing optimization, it is easy to get a gradient, right? It is easy, the term. So it is efficient to just get a gradient to optimize. This is one benefit of using linear models to respect to the weather vector. Okay? Okay, so this is the basic idea of the using linear model to deal with non-linear features, but still it is linear to weather vector, linear to feature structure. So difficult part is how to change the feature structure, add up the certain patterns, the term that can describe the property of a predicting task. Okay, so this is, we mentioned about the regression. So about classification. Remember, when we talk about classification, even the sign function, even the linear binary classification, the function itself is not linear to the input variable. So it is not, we do not say if the predictor is linear or not. We just talk about if a decision boundary is linear line or no. Okay, even the toy example we illustrated in previous part, binary classification, even the decision boundary is a line, still the predictor is not linear to the input variable. This is a sign function, right? Of course, to score function, it is linear, but to this sign function, it is not linear. So what we want to talk about, discuss in here is how do we design this classification, the decision boundary, to dealing with nonlinear features. Okay, so in here we can just for a circle decision boundary by simply to add up one term, square term, x1 squared plus x2 squared into the feature extractor. And then we can simply define a decision boundary, and that is a circle. Within the circle, that is positive class. Outside the circle, that is negative class. And still, we just simply use our sign function of score. The score is the inner product of what vector with a feature extractor. Okay, so but simply add one more term. And now this decision boundary is not a line, it is a circle. Still, what we need to do, just simply change one term of the feature extractor. Okay? Okay, this is how we deal with the feature extractor to deal with this nonlinear decision boundary. All right? this quadratic classifier. So since last week to now, what we introduced, we introduced basic idea of machine learning. Why we do that? And we design the linear models from regression and classification. And we talk about 3 different design choices, from hypothesis class to loss function and to the optimization algorithms with gradient descent and stochastic gradient descent. And then, of course, we have linear features. We have nonlinear features still. We can use nonlinear, we can still use linear models to deal with these nonlinear features. But the thing is, you need to well craft this feature extractor to well represent your features. And also we talk about the feature templates, the feature engineering part briefly. Okay? Okay. So these are for all today. And later on, I'll introduce a little bit about assignment for this semester. We have our first assignment and you have 4 weeks to finish it. All right? Okay. 10 minutes break and come back.